All right, our last section of material in section 3.7 is optimization. So often you get questions when you're working on difficult concepts of why am I doing this, how can this be used, and derivatives are no exception. This is an example of how derivatives are used to optimize results. So to give you an unrelated example, that is to say it's not related to the content you guys are going to do, my business calculus class works on optimizing business-related concepts. So their idea would be to optimize, right, to maximize, to get the best bang for their buck out of profit, right? If you're working in a business, you want the most profit possible. So you have to be really careful how you price your products and how many products you produce and how many employees you have in order to get that maximum product opportunity. And so that's an example in sort of the business world about optimization. We're going to look at more concrete engineering type examples in this class, but I just want you to know there are different kinds of optimization examples for different scenarios. So for what we're working on, some basic guidelines for optimization. They don't apply to every problem, but they do apply in general. So oftentimes it's helpful to create a visual, some kind of a graph or a sketch of what's happening. It might be a table of values of what's happening. And sometimes it's not. Sometimes there isn't a visual. But when there is, it's often a nice place to start. On the second one, to identify the quantities that are known and those that are to be found. In real life scenarios, often you have to identify what's not really necessary. You got lots of information in real life, and it really doesn't all apply to the particular problem you're always working at. Step 3, to write any applicable equations and figure out what it is you're trying to optimize. Are you trying to optimize area? Are you trying to optimize distance? Are you trying to optimize fuel efficiency? What is it in your scenario that's really the quantity you want to have the best result for? Step 4, determine the maximum and minimum allowable values, if any, for the variable you're using. So I mentioned something just a moment ago about fuel efficiency. If you were looking for fuel efficiency, obviously you can't have negative fuel efficiency, right? You don't get negative miles per gallon. It doesn't work like that. But there is also a maximum. I mean, like, you're not going to get 100 miles per gallon either. Right? There is a point at which that there is no ability to get something to happen. So there's often, almost always, sort of this boundedness to what you're looking at in a real-life problem. And then use calculus to find extrema. Now, you've been using calculus to find extrema. You've been doing it from a graphical perspective most recently, right? Looking for maximum and minimum points on a graph. But that's what you're going to do. You're going to take derivatives, you're going to set them equal to 0, and you're going to create sign charts, and it turns into the same kind of calculus problems you've been working. So we're going to do one that you've seen problems like this before, and you've probably seen them worked in different ways than what we're going to do, but it's a really nice example of how calculus can be used to find a quantity. So we're going to work with a fence. So you have a 3-sided fence to be built next to a straight section of river. Sometimes you'll hear these questions and they're on the side of a barn, on the side of a house, right? You're enclosing a garden to keep out, the dog or whatever, something like that. The enclosed area is specifically going to equal 1,800 feet squared. Okay, that gives you some boundaries of what you can and can't have happen. And we're going to try to find the minimum perimeter, right, the minimum amount of fencing, basically, that we need in order to create this enclosure. So our first step on these guidelines is to make a visual, and that makes a lot of sense in this particular one, to have a visual of what's going on. So that's how we're going to start. I have lovely tools to be able to create some imagery, so I'm going to do just a bit of that. So here's my river. And I need a fence. And as we're creating this fence, what do you think this fenced-in area should resemble? What's it going to look like in a real-life scenario? What shape? A rectangle, right? I mean, we don't make triangle fences. It's very seldom and weird. You're certainly not going to make a circle fence. That would be awfully odd, too, and really hard to manage. I mean, like, I don't even know how I do that. So, yeah, we're looking at a rectangle. So, we're looking at reasonableness of what's going on in order to create an image that makes sense. And it doesn't have to be perfect, but it gives us something to work with. I know that you know that in a rectangle, the sides we'll call this our width, are the same on top and bottom. And they're the same on left and right, except that it's a three-sided fence, so I only have one of the two sides that are vertically drawn. Okay? Now, if you were working with a rectangular enclosure that had all four sides, you'd have two of them, and that's fine. But this one specifically said we don't. And it also told us something that's a relationship between the L and the W here. It told us that the area is equal to 1,800 square feet. How do you find the area of a rectangle? Yeah, it's length times width. So this is something that we know. So this is a known quantity. We know that our area, A, is equal to 1,800. I'll leave the units off for now. And we also know that the area's formula is length times width, LW. If you want to use L's and W's, if you want to use X's and Y's, I don't care what variables you use. It makes no difference to me. But what this does is it creates a relationship between LW and 1,800 that says L times W is 1,800. Or, if you prefer, you could even solve for one variable, right? L is 1,800 over W. Is that okay? You might be thinking, well, why did she do that? Well, I'm going to use it in a minute. That's why. Having one variable solve for another is going to be a useful feature. So taking a look back up at our list of things, it says identify the quantities that are known. I did that. I know something about the area. I know something about the relationship between the length and the width. And it says, and those to be found. So what is it I'm supposed to be finding here? What is it? Say it for me loud, Eric. The minimum perimeter. In particular, I'm talking about perimeter that I'm finding, right? The minimum feature has to do with the fact that I'm optimizing it, so I will get to that later. But perimeter is the physical aspect I'm working on. How do you find the perimeter of an object? Really, any object in general. Yeah, in this case, because we're working the rectangle, we're adding the sides together. And we only have three sides, right? Because I only have a three-sided rectangle, three pieces of fencing. So my perimeter in this case is actually 2W plus L. I should have started with P equals. Let me shift that over. So that's my perimeter. Perimeter is 2W plus L. Does that make sense? Now, we've kind of been working steps 2 and 3 sort of simultaneously. We've identified what we need to find and we've created an equation at the same time. That kind of happens a lot. And Eric just a moment ago actually identified also what was to be optimized, which is the perimeter. He said we need to find the minimum perimeter. Now, the part that we haven't done is the very ending of part 3. It says write the equation in terms of one variable, right? So the perimeter, the P on the left-hand side is fine. It's the other side that's already written out here, 2W plus L, that has two variables that I don't want. I want it to only have one variable. So how can I change 2W plus L so that it has one variable instead of two variables? Right. We solved for L. And we found out that L was 1,800 divided by W. So we're able to change the equation into something that is a two-dimensional equation. I have only two variables, right? It's something that your calculator can deal with. You could graph this thing if you needed to for whatever reason, because I have P, our unknown variable, in terms of one variable on the right-hand side. So this is a good place to be. So we've finished step 3. Step 4 is to determine the maximum and minimum allowable values. What's the caps on this? All right, so if you think about perimeter, right, we're talking about, and actually we want the caps on the length and the width is what we're really working with, right? The perimeter will come in time. But what are some of our sort of high-end, low-end values that W could equal? And I'm specifically saying W because my equation is now in terms of W. So what value is sort of the minimum value that W could equal? Let me ask it differently. What can it be no smaller than? 0. I mean, it can't even really be 0 or I don't have area, right? So 0 is a good first sort of place for W to be? W's got to be bigger than 0, right? What's the high end? What's the cap that W could be?
1,500.
It's actually smaller than that, but that's a really good guess. Any idea what it has to be smaller than? It's not 1,800. Okay, I'll tell you what it is, but then you have to tell me why. It's 900. Yeah, because there's two W's. I have a W on the top and a W on the bottom. So at the very least, the 1,800 would have to be split between those two sides. And obviously that would still not create a rectangle. I'd have no area, but it is an upper end. So when I'm looking at a calculator screen, that helps me to know a minimum and a maximum Y value or X value, right? That's useful information. It also tells me, because on some of these problems, that if I get an area or I get a W value that's like 1,500, it doesn't apply to my problem. Okay, great, it worked out in terms of the mathematics for it, but it's really not answering the actual question that I'm working with, right? So these are going to be my limits on W, or my, my bounds on W. All right, last step. And this is the step, really what we've done so far is still nothing calculus. It's crazy, isn't it? The last step is the calculus step. It involves us actually taking a derivative, setting it equal to 0 or does not exist, and creating a sign chart. So taking a look at what we have, I need to take a derivative. It might be easier to think about the derivative if I write the equation like this. Okay. Most of our optimization problems are going to be friendlier in terms of taking the derivative. So that's actually really nice compared to, say, the last section where we were doing curve sketching and they were like all rational functions and they were just horrendous with their second derivatives going on and all that good stuff. All right, so we need a derivative of this. I almost said second derivative, but that's not right. I need the derivative of this. So what's the derivative of 2W? 2, yep. And then I need the derivative of 1,800W to the negative 1. Fantastic. I need this to set equal to 0 and to equal does not exist and all of that good stuff. A little bit of algebra cleanup will make my job easier later. So let me first write it like this. And one way or another, I'm going to have to figure out where this does not exist and where it's 0. Let me do the does not exist right now because it's the easy one. Where does this does not exist? Yeah, at x equal to 0, or not x, W equal to 0, but the reality is that we talked about before that W really can't actually equal 0 anyway, or I would have no area. So that is kind of irrelevant. It doesn't really give me any more information I already had. The equaling 0 part, though, is a little bit more interesting. So if I set this equal to 0, one of the things that you might do first is to put the pieces on both sides of the equation, or of the equal sign. So if I left the 2 where it was, and I moved my 1,800 over W squared like this. Now, when you're working with polynomials, and you're trying to figure out where they're equal to 0, we don't shift things over and factor. But I don't have a polynomial on this one. I have a rational function. And so I could have left it. There's a couple options. I could have left it like it was up here, found a common denominator, and that would be okay. We could do it that way. Or I can move it like I did, and we can cross multiply, and we can solve it that way too. And the reason that's working for us is because there's only one W in my problem, right? I can isolate W, whereas if I had like a W and a W squared, I would have my hands tied, and I couldn't do it that way. But the fact is I only have a single W represented here, which makes it easier to work with. I have more flexibility. So if I multiply my W squared to the other side, I have 2W squared equals 1,800. Then what? Yep. Okay, so I'm going to move up here. Close. Right. Okay, so I've got W squared equals 900. And then Emma said take the square root, which is correct. Now, technically, this gives me two answers because I took the square root. But the negative, say that louder, Eric. It cannot be negative. I'm working with a physical width quantity that can't be negative. So I only end up with the positive part of this. So what is 900 square rooted? What's the square root of 900? 30, good.
Actually, I have a question on that.
Yes, sir.
So like on the test, like I know I didn't need like a negative or something like that, like a negative version, so I just didn't, I got taken off of that. So I was confused, like, do we need to still write plus or minus the density?
Let me see what you're talking about because I think there was something else going on that caused that to be a problem. So I think that's a slightly different question. You're just remembering the negative positive feature of it.
Okay.
Yeah, let's chat about it. Let's look at your test again later.
Okay.
Emma?
Sorry.
Here, there you
Well, and there also just so happen come across times where there's negative under the square root.
Yeah, so I think that happened on your work last night. Does that sound right? Where you had some negatives underneath radicals?
That, and there's also been a few other times on my homework, but just have to.
Yeah, that's a good question. So one of the things about negatives underneath radicals is that calculus, the calculus that you're learning right now anyway, is done with a real number system only. So anytime you have a negative underneath the radical, it's giving you an imaginary or a complex solution, which is non-real, which is why it doesn't apply to what we're working with.
So then, well, if you come across that though, would that just be a D&E?
Yeah, it would. It would be a location where it doesn't actually result in any values that would give you a solution.
Okay.
Mhm. Yeah. Okay, W is 30. We definitely need to verify, though, that this gives us a minimum. Because it could be giving us a minimum, it could be giving us a maximum, or it still could be giving us simply just one of those places where it flattens out and doesn't give us anything of value. Are you with me? So this is the part people usually forget on optimization, is verifying that it really gives you a minimum value. And the way that we've done that, there's a couple of ways. Actually, I can let you pick. One option is that we can find the second derivative, and then we can plug in 30. That's one option. And if it's positive, it means that it's concave up and I have a minimum. If it's negative, it means it's concave down and I have a maximum. That's the second derivative test. The other way that I can do it is I can set up a sign chart with 30 on my sign chart, and I can test a number before 30, test a number after 30, and see where things are increasing and decreasing. What do you guys want to do? Damon's strongly going for second option. I could see that really. Are we good with that? Okay. So if we take a sign chart and we put 30 on there, we need to test a number in each interval aside from that, but we need to remember that we can't go below 0 and we can't go above 900. Those are the endpoint caps for what we're working with for context of this problem. So what number would you like to test? 10 sounds great. And another number? 50 or 100. Okay, pick your favorite. And we're going to plug these numbers in where? The derivative. Very good, Parker. So my derivative in either version are down here. So pick your favorite. We're going to plug in 10 and find out, do I get a positive or negative? We're going to plug in 50 and we're going to find out, do I get a positive or negative? So let's check it out. Did you get values already, Damon? What do you have?
I got negative and then positive.
That's what I have as well. Got a couple nods. Okay, good. So negative means it's decreasing, right? Downhill. Positive means it's increasing. So what's happening right here? I have a minimum. So this is my verification that I've really found a minimum. We haven't quite answered the question just yet. The question said to find the minimum perimeter and the dimensions. And all I have found so far is what? W. W is 30. Okay, so I'm going to write, I've got space over here. What I know so far that W is 30. I need to find my length, and I need to find my perimeter. So how do I find length? Right. 1,800 divided by 30. What will that give me? 60. Okay, so this is telling me now my dimensions. So my dimensions are 30 what? Feet. So 30 feet by 60 feet. And then does that, in fact, it's always a good check. Did that give me the area I was supposed to have? It did. Okay, just checking. And then I need the perimeter. So what is the perimeter? That is the amount of fencing in this case. How much? 120. And how did you get 120? Excellent. So I'm going to write that down. You had two lengths of 30 plus the length of 60, which gives you 120. 120 what? Feet, right. So this is my perimeter and my dimensions, and I solved the problem. I realize that I show a lot of work. You don't have to show every single step that's on here. But there better be enough that I know that you know what you're doing. You can't just hit on 3 little pieces of this and find the answer. That's not going to work, okay? All right, let's try another one. This is one of my favorite optimization problems. Another classic one. Yes, Jared? Yes, sir. This one or the one before? Okay. You good? Okay. All right. A box with no top is to be built by taking a 6-inch by 10-inch sheet of cardboard and cutting X-inch squares out of each corner. Folding up the squares, or folding up the sides. Find the value of X that maximizes the volume of the box. So the picture you should have in your mind is like a shoebox. And if you were to take a shoebox and you were to flatten it out, it would be two-dimensional, like a two-dimensional piece of cardboard, right? With the corners missing. Does the visual make sense? So if you're starting from scratch the way they described it, here's my note sheet. If I were to take my note sheet and I were to cut a corner out of each of these, right? Cut each of the corners out, and I were to fold them up, I would create a box. It would be able to hold something, not much because this is a flimsy piece of paper, but a stronger piece of cardboard or something like that, it would. We can fold it up. And what we're trying to figure out is how much of the corners should be cut so that we get the most space possible in the box. Because you've seen shoe boxes that are really thick and deep, right? And you've seen them that are really wide or really long. And yes, they need to fit shoes in that particular case, but if you're simply looking for volume, like maybe you're just going to fill the thing up with marbles, you don't really care what the shape is per se, you want the most space for the marbles, that's the problem we're working on. Okay, does everybody have an idea of what's happening? Okay, this is a very classic problem. Every calculus book will have this problem in it. Okay, so a picture is a good place to start, just like on some of the other one, the last one even that we just did. So I have the advantage, of course, of having my rectangles to be perfect. It's a very nice advantage. And I can draw a little box in each one of my corners, too. So here's the little box that it's talking about. And I have a corner like this in every, I have a dotted box in each of my corners. And what we're doing is we're going to cut that out. Like you're physically going to cut along the dotted lines. All right, so those are going to be cut. And then what you're going to do is you're going to fold. And you're going to fold along my red dotted lines. And when I fold along my red dotted lines, the red rectangle in the middle is now the bottom of my box. And the tiny little rectangles on each of the 4 sides are going to be the sides of my box that are folded up. Okay, all good? It's important to realize that those little corners have to actually be squares to make this work. Otherwise, like the length sides that fold up might be taller or shorter than the width sides, which doesn't help me out. So I really do have to have squares in each of the corners, even though my original box is a rectangle. And just to get some of the other details on there, the box itself was 6 inches by 10 inches. Like that, right? Okay, I want you to think about the little red rectangle, smaller, not little, but smaller red rectangle in the middle. And what I need to know is I need to know, not in terms of a concrete number, but in terms of an expression with algebra, what are the length and the width of the rectangle that's red in the middle? So let's start with this one right here first, the width. Did you have an idea? 6 minus 2x. I think that's what I heard. Does that, yes? Did you say 6 minus x? And somebody else 6 minus 2x?
X squared, there's 2 x.
Ah, but do you understand why it's 2x?
Yeah.
Okay. All right, so we had a length of 6, and then we chopped off an x from the left side, and we chopped off an x from the right side, which means we chopped off 2x. So it's 6 minus 2x. Now, given that we've done it once, we should be able to replicate that idea, and what would be the length of my box? Yes, 10 minus 2x. Okay, how do you find the volume of a box? Right. Length times width times height. All right, so let's go back and make sure that we've hit sort of the ideas of what our question or our guidelines here. We've created a visual. We've identified the known quantities in terms of the visual, like we've put them on there, right? We've written some equations or some expressions about what's being optimized. In particular, it said that we're supposed to find an optimized or a maximum area. Volume, and so we found the volume. And then it says that I'm supposed to take that volume equation and write it in terms of one variable. And right now I have 3, L, W, H. And none of them are actually on my picture, right? L, W, or H. So thinking in terms of the box, not the original sheet of paper, but the one that's been formed by folding up my corners and all that good stuff. What is the length of the box?
10 minus 2x.
Right, it's 10 minus 2x. What is the width of my box? 6 minus 2x. Now, we haven't even talked about the last one, but I need to know what's the height of my box. It would just be x, right? It's the part that folded up. And the part that folded up, I didn't write this here, but it has length x, right? I won't write it on all of them, but those are all lengths x. Fantastic. So the cool thing is that now is an equation in one variable on the right-hand side. Yeah, I've eliminated it down to one variable. And I'm ready to use some, well, let me stop just a second. I almost skipped it, and it's important that we do it. I need to make sure that if there's any sort of maximum or minimum allowable values for what's going on for, in this case, we're identifying x, which is the width of the cut, right? So what is the smallest value x could not, or could be, but it can't really be it? It's 0. So just like on the last one, right? My bounds for x. It can't be any smaller than 0, and if it were 0, I'd have no volume at all. What's the biggest that x could be? What can we not exceed? 3. And how'd you get 3?
Half of 6.
It's half of 6. Because I'm cutting x from both corners. There's 6 across. It's half of 6. If I actually did that, I'd have to fold it up and it'd be a V shape, right? Which would not create a box either. But yeah, so my answers, whatever I find, need to be between 0 and 3. Very good. Last piece, which is the calculus piece, is to actually find this maximum value. And we do that with calculus. Now, this is a messy expression in the sense that there's 3 pieces, right? But in the sense that I can deal with them, it's actually pretty friendly. What could I do to make this problem easier to take the derivative of? Connor? Yeah, make it a polynomial by distributing is what you mean, right? Clean it up. Just distribute it all out. Absolutely. So I'm going to distribute this x through at the end, but I'm going to deal with the binomials first. So I have 60 for the first terms. The outer terms I have negative 20x. My inner terms are negative 12x, and then my last terms are positive 4x squared. And then all of that's times x for another time. So I have 60x. I have negative 32x squared, and I have positive 4x cubed. Okay. Does that look all right? I think that's what I have on my paper too. Okay? And you know what? I'm pretty sure that at this point, all of you look at that and say, I can do that derivative. I like that one. No problem. So we're going to do that. We're going to take the derivative. So what's the derivative of 60x? 60. 32x squared. Negative 64x. And 4x cubed. 12x squared, right. What kind of an equation did we end up with here at the end? It's what? It is a polynomial. Does anybody have a more specific type of polynomial that it is? It's a quadratic, or you can say visually speaking, it's a parabola, right? So as I set this equal to 0, I could get no solutions. I could get one solution, or I could get two solutions. And as I look at my solutions, I still need to make sure that they're between 0 and 3, or they're really not a solution to my problem. All right? So we're going to set this equal to 0. One thing to realize before you try to work too much with solving a quadratic is that if there's a factor they have all in common, get rid of it. Make it easier on yourself. Do all of these terms divide by something? 2, bigger. 4. They're all divisible by 4, and at least, even if I have to go working with quadratic formula, I want to work with smaller numbers if I can. So it's going to be useful to us to go ahead and divide by 4. So we're going to divide, it's really both sides by 4, but dividing 0 by 4 is super unexciting. So I have 15 minus 16x plus 3x squared equals 0. And this is probably my first bad news for you of the day, at least, you know, math related. This does not factor. Yeah. So we're going to use quadratic formula, all right? So we haven't done that in here, or at least not in a while if we have done it. So we're going to use a quadratic formula and remind ourselves how that looks. So x equals negative b, which would be positive 16, plus or minus the square root of b squared, which would be negative 16 squared, minus 4. My a is at the end because it's the x squared term, right? A times c, which is 15, all over 2a, which is 2 times 3. Sorry, I could have put those in descending order of exponents, and I didn't think that it would matter. Hopefully it's okay. All right. But are you ready for the cool answer about this? Yep, Eric.
But the only okay with it, like in a test, if we only write out the formula to show that we're doing this without insert all the values and that's fine.
I want to see the values inserted, but then after this, you can put all this in your calculator and let it do all the simplification. So what I just wrote down, I want to see, but then after that, you don't have to show me any more steps. At this point, once I've written this down too, and you can plug it in your calculator, I'm good with decimals because we're working with an optimization of a real life situation. And if you were real life talking to me about what this answer is and you tell me radicals, this doesn't make sense. So we're going to simplify this and get a decimal approximation for an answer, 2 decimal places, unless it asks for something different, like on a, a web assign or a problem on your test or something like that. There are 2 answers that come out of this. So what answers do you guys get when you use the positive versus the negative in the equation?
Positive is 4.119 and negative is 1.213.
Okay, so I have 4.12 if I use 2 decimals, and I have 1.21. But do I really?
No, you don't need a 4.1.
Right. The first one, the 4 one, it doesn't work in the context of the problem. So I don't need to consider it. Because my bounds up here are between 0 and 3. So I really only have one possibility, and that possibility is at approximately 1.21. So you guys told me last time you wanted to do a sign chart, so we'll do another sign chart. So here's 1.21. And again, you need to bound it between 0 and 3 so that you make sure you choose values that are actually on the intervals you think you're working with. Okay. 1 and 2, okay. So we're going to test 1 and test 2, and we're going to plug those numbers into the derivative. And you can plug it into this version if you wish, or into the version that's divided by 4. It doesn't matter. So if I plug those numbers in, what happens in terms, is it positive or negative, when I plug in 1? What is it? It is a positive, and then at 2 it's a negative. That's right. Positive means increasing, negative means decreasing, so what happens at 1.21? There's a maximum, which is what we were trying to find, was a maximum volume. So we've done the calculus part. We need to make sure we've actually answered what we were asked to find. It says find the value of x that maximizes the volume of the box. It could say find the volume of the box. It didn't. It just asks for the value of x. So x is 1.21 what? Inches. And we're done. All good? Okay. We have one more. Also an interesting one, very classic. You see it in most calculus books. We have an equation given to us, and it wants us to find a point that is close to another point on the graph. The tricky thing is that it's a curved graph, right? It's y equal x squared, and so it's not so easily direct, like you can't just answer that super directly. I do have the ability to draw a graph of this one nicely enough, because I have an equation. So, oops, that didn't change it. So if I'm drawing y equal x squared, you know that that's a parabola, roughly speaking like this, right? And I want to get close to the point 0, 1. So if I sort of put some hash marks here on my axes, 0, 1 would be right here. It's a terrible color. Let's try something else. How about that one? That's worse. Oh my goodness. How's the orange? That should have better. Okay, so this is the point 0, 1. So obviously if I went from 0, 1 straight down, how far is the vertex from 0, 1? It's 1. So this distance is 1 away right here, yeah? And if I went over to this point on the curve, how far is it over? It's also 1, right? So whatever distance I'm getting, it better be somewhere that's happening, sort of visually speaking, in between this point and this point, because if I go straight down, I get 1, straight over to the left and to the right, I get 1. So there, the answer needs to be, I mean, it should be somewhere over here. There should be some space over here that's a little bit closer to the value, to the point that I've got anyway, than the value 1. So can you visually see what they're asking you to find? Okay. So we have an equation. Our equation is y equal x squared. We have a point. The point is 0, 1. We've drawn our picture. We've identified what we know. We've placed them on the graph. And we've kind of talked about the fact that we need to find the point that's sort of, that I drew in that red area, right? And it's similar, I mean, it's a symmetry argument that there's 2 points that are answered to this question, right? The one that's on the right-hand side where I drew the dot and the one that's on the left-hand side where I haven't. But there's going to be an equal distance point over here. I'm going to get 2 answers. Everybody good with that? Okay. And I need to find, or I need to minimize what? What you're measuring. What do we call that? There's a word. Distance, right? I'm trying to minimize distance. So I need the distance between this red point that I don't know where it is and the point 0, 1 that I do know where it is. Do you remember the distance formula? We'll just start with the general formula for the distance formula.
Square root.
Mm-hmm.
X minus X. All that squared.
Mm-hmm.
Minus Y.
Good job. Do you guys remember that? Like from way, way, way back in the day? Maybe it's been a while. But yeah, it's a distance formula. And some of the distance formula you already know. In particular, I don't care which one you pick it to be, but you know one of these XY pairs. It's 0, 1. Right? So let's start filling in what we do know, and we'll figure out the pieces that we don't. I'm going to put the part that I do know as the second piece of the subtraction, so the x1, y1. So x1 is 0, and y1 is 1. So this is what I have so far. And the red point that I don't know, this red point right here that I'm looking for, is the point x, y. It's what I don't know. But there is a relationship between x and y. What relationship exists between the x value at that point and the y value at that point? Did you have it, Lexi? No? Sorry, I thought you were saying it. What's the relationship between the x coordinate and the y coordinate at that point? The equation, right? Whatever x is, y is that value squared. I said that backwards, but yeah. There's a relationship that says x is equal to y squared. So, down here, x is x, and what is y? X squared. It's the same thing that happened on the earlier problem where Emma said we can plug in the value we already solved for. We have an equation that tells us how x and y are related in terms of what y equals in terms of x. Y is x squared. So over here in my equation that I'm trying to create, x is x, and y is x squared. And that's what I have. And the beauty is that at that point, I only have one variable again on the right, which is really my goal as I'm trying to evaluate pieces of this together. And it looks worse than it really is because if I clean it up, some of the pieces clean up very nicely. For example, the first part is simply x squared, isn't it? Because I have x minus 0. Second part, not quite so friendly. I have x squared minus 1 squared, which would be x to the 4th. And if I FOIL it out, I get minus 2x squared, and then plus 1. Okay, and all I did for that was multiply out x squared minus 1 times x squared minus 1. And then I can distribute my negative through. So I have x squared minus x to the 4th plus 2x squared minus 1. Still working algebra here to clean things up. I have negative x to the 4th, positive 3x squared, and minus 1. There's an error. I'm sorry, one fix. It's like this isn't where I got my notes. This should have been added together. They aren't subtracted, they're added. Too many negatives going on. So let me fix this step. Sorry guys. Should have checked in with my notes sooner. This is positive in the middle. Positive at the beginning. And I have a negative, more than that, a negative x squared right there. Okay, I think I fixed them all. So sorry. Those little sign errors get you every time. Okay, and because I'm going to take a derivative here in a minute, it might be useful to remember that this can be written to the power 1/2. Right? So, We do need one more thing. We do need an upper and a lower end on what's reasonable for our problem. What we're finding, what x is in my equation is x is the actual x coordinate that I am at on my graph. So thinking back to the actual graph and what I've drawn, what is the low end for what x could be, and what is the high end for what x could be? What values am I looking between? 0 and 1. So my bounds on x are 0 to 1. Right? It's kind of the first and the last red dot that I put on the either side of the red dot I'm really looking for. So we are ready to do a derivative. D prime. How do you do the derivative? This is the messiest derivative we've done compared to the last two. How do I do a derivative of square root or x to the fourth minus x squared plus 1 to the 1/2? 1/2, what's next? Rewrite what's in the parentheses, good job. To the power and negative 1/2, lovely. And then what? Right, and then the derivative of what's inside, so that's 4x cubed minus 2x. Oops, and that's it. Okay, I think I got them all. We're going to eventually set this equal to 0 and solve, or equal to does not exist and solve. So cleaning it up will help a long ways towards that. Means I know I have 4x cubed minus 2x on top. I have a 2 on bottom, and I have a square root of x to the fourth minus x squared plus 1. Do you see any other simplification that could be done? There is one more thing. Factoring out a 2. There is a 2 in each of these terms that I can simplify and reduce down to give me 2x cubed minus x over the square root of x to the fourth minus x squared plus 1. All right. The square root would have problems anytime we're dealing with negatives underneath it. Like those are legit possibilities, right? There's a domain issue there and so forth. The numerator is where I'm going to get my x equal to 0 locations. So let's focus on that for the moment. If I were to take 2x cubed minus x, and I want to know where that is equal to 0, this is one of those locations where I do have x's in 2 locations, so you can't move them to the other side of an equation and work with it that way. It's got to all stay on the same side. It has to be factored. So what can I factor out of 2x cubed minus x? And x. And then I have 2x squared minus 1, like this. X can equal 0. Because there's only one x inside here now, you can also set it equal to 0 and then move things around to solve. So here I have 2x squared equals 1. X is equal to 1/2. And then take my square root. So again, this is one of those scenarios where I have a positive or a negative, but do I really? I mean, I do, but it doesn't. We got to be careful, right? So I am going to get a positive or negative here. I've made my bounds on x up here from the picture as 0 to 1. But I realize that there's a symmetric argument on the other side. So there really is another x value that's going to work, because once I get the positive x value, the negative x value is going to be the exact same thing, whatever it is. So if it's a positive, 0.2, I'm going to have a negative 0.2, and I'm going to get 2 answers. So for now, let me go ahead and leave the positive or negative on there. Square root of 1/2 is the same thing as the square root of 2 over 2, if we rationalize it. Okay, so taking a look at my interval, I have a bound of 1, and I really should have written this as a bound of -1 because I've got symmetry. And I've got that square root of a negative square root of 2 over 2, and I have a positive square root of 2 over 2. And I'll go up and I'll adjust my bounds to actually say that I really can go to -1, I just have symmetry. And I could focus on 0 to 1 if I want to. Same things are going to happen. So we need to test some numbers in each of these intervals. So does anybody know what square root 2 over 2 approximately is, just for a reference point? It's about 0.71. Okay, so we need numbers that are on either side of about 0.7. So maybe you try them in between point, you try 0.5. So maybe you try 0.5 in here. And negative 0.5. And then maybe you try 0.8. I don't know. You get to pick a negative 0.8. And you're evaluating them into the derivative. In its most simplified form, it was this one that I've boxed in red. And you want to know, do I get positives or do I get negatives? So what happens if I plug in negative 0.8? You get a negative. How about negative 0.5? It's a positive. What about negative 0.5? I'm sorry, positive 0.5. It's a negative. And 0.8, it's positive. So I have decreasing, increasing, decreasing, increasing. And let's talk about what happens at each of these locations. What happens at negative square root 2 over 2? It's a minimum, so I have a minimum distance. What happens at 0? There's a maximum distance, but we already kind of knew that, right? I'm as far away as I'm going to get in this sort of cupping area on the bottom of the graph. And then what happens at square root 2 over 2? Another minimum, right? Yeah. So we are supposed to find what? Find the point on the curve. Points have an x and a y ordered pair, just like this point did, right? It's 0, 1. And what we just found out was 2 x values for it to be a closest value, so we found a minimum, that's what we were finding. We found the x value of square root 2 over 2 and the x value of negative square root 2 over 2. But I need the ordered pair. I didn't find an x value and a y value. I found 2 x values. But I need the y value that goes with each of them. How do I find that? Squared. The x value. Right, exactly. The equation has to be satisfied still. Y is still equal to x squared. So if I were to take the square root of 2 over 2 and I were to square it, I would get 2 over 4, which is 1/2. Yes, I would. And the same thing will happen with the negative, right? I will still get a positive 1/2 because I'm squaring and it will become positive. So I have 2 points that are at minimum distances. Negative square root 2 over 2, 1/2, and positive square root 2 over 2, 1/2. And I think that square root 2 over 2 is a value very familiar with from trig. Where did you encounter square root 2's over 2's? At pi over 4 or 45-degree angles, right? So think back to your picture. Does it make sense that that would be happening here again as well? Yeah, that's the visual you've got going on. So it's a very reasonable answer for our question. All right, we have 15 minutes to take a look. There are 4 written work problems here. If you would like to start with not the first one, that's fine. Just make sure you label them very clearly if you and somebody else that you're working with would like to start somewhere else. And let's get started on those.